So with our motion problems, we've been bringing everything back to the forces. Force is, of course, mass times acceleration. So we're interested in the acceleration that happens in this circular motion. So we're looking at uniform circular motion. So basically constant angular velocity. So it's just going around with constant angular velocity. Now it would be simple, I guess, to say, oh, well, if it has constant angular velocity, then the acceleration surely is zero. But it's not. The linear velocity stays constant. Because remember, v equals r times omega. So if omega is constant, the linear velocity is constant. And so, yes, you would think acceleration is constant as well. Problem is, there's directional change. So let's draw up a picture so I can show you what I mean. So A is going to move to P with a constant angular velocity. Okay. Well, if it's a constant angular velocity, remember we said the angular velocity, the linear velocity was directed at the direction of the tangent at the particular point. So the acceleration will be the change in velocity. So at A, I'm going off in this direction there where the blue line's going, with a velocity of v. At P, I'll be going off with a velocity of v dash. Now, if we think of those as vectors, now the length of the vectors are going to be the same because the actual magnitude, the velocity, is constant. But the direction that those vectors are going in are different. So if I was to draw up a diagram, here we go, then that red vector there must be the change in velocity. My initial velocity was going this way, to the left. My final velocity is going to the right. So I've ended up, if you like, going from the tip of that vector to the tip of that vector. That must have been the change then, how I've changed. So there is a change. So if there is a change in velocity, then there is an acceleration. Now, because we know the magnitude of those blue vectors are the same, I know that it's an isosceles triangle, and that angle there will turn out to be theta, because we could play around with similar triangles here. We know this is also an isosceles triangle. It's going to be similar to triangle AOP, and we know the angle at the centre of that one's theta. So all right, let's have a look at these two triangles. From here we're going to come up with an acceleration equation. So the change in velocity, I'm just looking at the ratio of sides in similar triangles here. So the one I've labelled change in velocity over AP would be the same as V over R. Rearranging that, I get that the change in velocity is equal to V times AP over R. So we know acceleration is the change in velocity over the change in time. So our acceleration, now I can write it down. Oh, it's going to be V times AP over R times the change in time. Now remember, we're talking about circular motion, so that change in time is approaching zero, because you're just constantly changing direction when you're going in a circle. So that delta t must approach zero. But also, if it's approaching zero, the length of the arc would be the same as the length of the chord, because you haven't really moved. So it would approach, as it approaches zero, AP would equal the length of arc AP. So let's rewrite that then. So the acceleration will be the limit as time approaches, or change in time approaches zero. Velocity times the length of the arc AP over R times change in time. We also know distance equals speed times time. So the distance, the arc of AP, must equal velocity times the change in time. So let's sub that in. The change in times cancel, and we end up with V squared on R. But remember, we said V was constant. The radius is also constant. So the limit must be V squared on R. It's just that constant value. So there's our acceleration, V squared on R. So right, that's where it comes from. So acceleration in uniform circular motion will always have magnitude V squared on R. The other thing is the direction of that vector. Well, that vector, again, we can play with the geometry of it, but we can show that, hey, that vector is always going towards the centre of the circle. That change will always be going towards the centre of the circle. So, acceleration involved in uniform circular motion. Acceleration is v squared on r. Of course, I could write it this way as well. If I was talking about angular velocity rather than linear velocity, I'll just substitute in v equals r omega, tidy it up, and I get acceleration as r times omega squared. So depending on how we talk about velocity, linear or angular, which formula we would use. But I said we were interested in forces. Well, force is just mass times acceleration. There we go, that wonderful formula. The force is mv squared on r, or mr omega squared, depending again whether you're talking about linear velocities or angular velocities. So all right, here is what's getting quite an old question now. 2003. Particle of mass m moves with constant angular velocity omega, and what they've basically done is given us the parametric coordinates of a circle. Because if we're moving around in a circle, then the position on the point of the circle would basically be the parametric coordinates of the circle. So x is r cos theta, y is r sine theta, theta is omega times t. Show that there is an inward radial force, that's just basically saying it's directed towards the centre, of magnitude mr omega squared. Now, you don't have to do it the way I just did it. I just build it up from first principles there. We can do it with what we already know and with the parametric coordinates, so let's do it that way. This is probably an easier way of doing it than what I explained before. So, there's our point, random point on the circle, got its parametric coordinates. So I know x is r cos theta, y is r sine theta. Okay, I'm just going to work with the horizontal components and the vertical components and then resolve them. So horizontally, the velocity will be minus r sine theta, but it's got to be times the theta to t. I've got to differentiate implicitly here, because I've got to differentiate with respect to theta, but I want it with respect to t. So using implicit differentiation, chain rule, call it what you will. But to theta to t we know is constant. To theta to t is omega. So I could rewrite that as minus r omega sine theta. Vertically I can do a similar thing. Differentiate r sine theta with respect to theta. We get r cos theta times the theta to t. But the theta to t is a constant, omega. We get r omega cos theta. So now we'll find the accelerations and something lovely happens. Acceleration minus r omega cos theta to theta to t. Again, the theta to t is omega. I get minus r omega squared cos theta. But look at what we've got. X is r cos theta. I could rewrite the acceleration as minus omega squared x. There's something we recognise. Simple harmonic motion. That's what I was saying before. Circular motion is simple harmonic motion. It's simple harmonic motion horizontally. I can do the same vertically. It's simple harmonic motion vertically. And a circle is symmetrical over, so really it doesn't matter where you look at it, it's always going to look like simple harmonic motion. Okay, let's resolve these accelerations to find out what our acceleration is. Okay, bit of Pythagoras. So I'll say the acceleration squared is the horizontal acceleration squared plus the vertical acceleration squared. And I end up with omega to the power of 4 times r squared. Because x squared plus y squared is the equation of our circle. There it is. A is r omega squared. Now the angle alpha will be the direction of the vector. It not only asked us to show it was r omega squared, it asked us also to show it was going towards the centre. Okay. Oh, sorry, it was the force they asked us to find. So what? Multiply it by mass. You get the force. So we inverse tan of y double dot on x double dot. Well, look what happens when I substitute in minus omega squared y and minus omega squared x. They cancel, and it's the inverse tan of y on x. Which, of course, if we go back to our original diagram, it's the angle going towards the centre. It's theta. So that proves the second part. That's probably how I would have done it that year in the exam, rather than building up from scratch like I did it before. So yes, there is a force, mr omega squared, and it is acting towards the centre. One of those pesky satellites up in orbit at some disputable radius. We'll just call it R, makes life easier. Constant velocity, And gravitational force at that point is am on r squared. A is some constant. We need to show that r is the cube root of a on omega squared. Good old Bob. Bob the satellite this time. Okay. The resultant force. The resultant force in circular motion is always that centripetal force. Okay. So the resultant force, yes, mx double dot, but I can replace it with mr omega squared. It's always the result of circular motion. What forces do we actually have? Well, the only force we have is am on r squared. So when I resolve my forces, the resultant force, this time it's positive. Because the other thing about centripetal motion, it's always directed towards the centre. I can't choose positive and negative with that one. It's always towards the centre. Now, if you think about gravity in this case, well, gravity will also be towards the centre. So they're both positive. mr omega squared will be am on r squared. It's now just a matter of making r the subject. And it comes out quite nicely, really. So r cubed, there it is, the masses cancel, and we have our answer. We have our answer there. Let's look at something a little bit more interesting. I have a string, it's 50 centimetres long. I know it will break if I put a mass exceeding 40 kilograms on it. It'll just break. So I'm only going to put a mass of 2 kilograms on it. But now I'm going to have some fun with my piece of string. I'm going to spin it around in a horizontal circle around my head, just for the heck of it. Basically, the question's saying is when will the string break? Like how fast could I spin that before the string breaks? All right, there's good old Bob. In this case, Bob's at the end of a string. Bob is the mass. My resultant force, I'm going to say it's going down in this one, because at the moment it's not doing any motion. It's just hanging there on a piece of string. So I could, if I want to, define the resultant force to be up or down. Doesn't matter. I'm going to define it to be down for this one. And we know we've got mg, but that's all. Or is it? There's always resistive force. So now to introduce, for those who don't do physics, a new force here, which is called tension. Whenever you have a string attached to an object, there will be tension going away from the object, so going up the string. So that's a resistive force. So I have this in addition. So my resultant force will be mg minus whatever the tension in the string is. Divide through by mass, although in this case I've also substituted in, you'll notice, for the acceleration, because remember, it's just hanging there. It's not moving. So the result of this thing is nothing. It's not doing anything. So I can substitute in for the resultant force of 0. That allows me to work out an expression for tension. Tension, well, we were told it's a mass of 40 kilograms, and gravity we're assuming is 9.8. So we know that when the force on this string is 392 newtons, that's when it breaks, regardless of the size of the mass. Just 392 newtons. So now, what happens when I put a 2 kilogram mass on it? But now I'm spinning it in a horizontal circle. So here's my horizontal circle. The resultant force must go towards the centre. It must go towards the centre. Horizontally, there'll be tension up the string. But that'll be the only force on this particular object. So my resultant force, which is always centripetal force in circular motion, will equal the tension. So tension will be mr omega squared. We know it can handle a tension of 392 newtons. So 392 newtons, a mass of 2. The length of my string is, 50 centimetres, but we've got to keep the units consistent. So 0.5. Now, how did I know I had to put it into metres? Anyone care to explain why I had to use metres over there? Well, actually, yes. I guess you could say that because of gravity. Because remember, tension 392, we worked out back here, using gravity, which is 9.8 metres per second squared. Got to keep your units consistent. Also, you can think of the units of newtons. Newtons is equal to, what is it, kilograms metres per second squared? Yeah. So omega squared, and there it is. So 2 root 98. But remember, I've substituted in for angular velocity, which is good. That's what they've actually asked me for. So great. Radians per second is what I want my answer for. If they'd asked the linear velocity, then I'd have to go, well, V equals R times omega. Or, of course, I could have used mv squared on R here instead. So 9b, we'll have a go at those Patel ones. I know I'm saying all there and you're thinking, oh, all of it. They are very short exercises in Patel. There's not a lot of questions in there. And we'll grab a handful out of Cambridge as well. So.